we barely started osmosis, barely. Any questions from last week? Actually, on anything from last week? I've already had several questions about the peptide bond and everything. Everybody okay, basically? Okay. Let me just remind you where we left off. I was going to do, or I was doing, a beaker with two solutions actually. This semi-permeable membrane down the middle, which remember for biological organisms, that's us. It's a cell membrane. And here, 5% glucose solution, and here 10% glucose solution. Well, I forgot one more thing, by the way. For our lab on Thursday, technically you really don't need the lab manuals, because Thursday is just a get acquainted type thing. We'll be learning how to use the microscopes. And I know that most of you have used microscopes already. I know that. But these are actually pretty nice microscopes. So really we'll just be looking at slides, looking at some pond water and so on. And like I say, just getting acquainted with things. You really don't need your lab manual for that. On the other hand, I'll be telling you what to fill in for the lab reports. That will be due the following Tuesday. So you might want to bring it for that, just to see what to fill in. But in terms of actually doing things, you won't need it. Starting next week, we will need them. Yeah.
And the lab report is the report?
Yes.
Okay.
Yeah. So anyhow, so for Thursday, 2 days, you can bring them and not as you wish. Okay, back to this. So 5% glucose, 10% glucose, and normally you would expect your high concentration glucose to diffuse into the low concentration area, but it won't because of the cell membrane, or I will say more generally, the semi-permeable membrane. That will stop the glucose. So we have an imbalance between the two sides. Nature does not like an imbalance. So basically, and this is where the semi-permeable membrane comes in. Basically, if the glucose cannot move, the water will. Now, the way I do this, it's a little bit odd, but it works. 5% glucose, it's the same thing as saying 95% water. Now, you don't normally speak or think of a water solution. That's why it's a little bit odd. But it works. So this would be 5% glucose is 95% water. And the 10% glucose %90 water. So what we have now are two concentrations with a high water concentration and a lower water concentration. You would expect, based on this, for the water to flow from left to right. You'd expect the water to flow from a high concentration into the low concentration. That's the diffusion. The diffusion of water through a semi-permeable membrane. So like I say, it is odd, to talk about a water concentration. It works. So 95% water, 90% water, you expect the water to move from high concentration to low concentration. That's diffusion. And I'll exaggerate a little bit. What you should get here is something like that. And it's going to go until the concentration balance. Like I said, I've exaggerated a little bit. But essentially, the water is going from left to right. So the left side is losing water, and that's this. The left side is losing water, and becoming more concentrated. The glucose isn't moving, it's the water. So less water, same glucose, more concentrated. Over here on the right side, you're adding water. So you're doing the same thing as diluting. You're diluting the right side. So therefore, you're going from 10% down to a 7.5%. That's osmosis.
I don't get the right side.
Pardon me?
I don't really, what's the difference of the right side and the left side? 'Cause
Well,
That's
you're
like
starting here
7.5.
on the right side here with 10%.
No, I mean that one.
Up here?
It says 7.5%.
Yeah, 7.5%, because you added water. So you did have a 10% glucose, you added water,
Yeah.
which means you diluted it.
Right.
So if you're diluting, you're lowering the concentration,
Oh.
and that's what that is.
Oh, duh.
So does it,
Help her along. Yeah.
so does it depend on how much water you add?
Well, it always would, because, you know, with anything you do, the more water you add to anything, the more you're diluting.
So like,
But in this case,
first one's
the water flow will
facilitated,
continue until they balance.
Facilitated, you need a carrier. No, the first one
If
is
they don't
diffusion.
balance, then they're still getting
So this is
imbalanced.
diffusion,
They
this is
still have
osmosis. He hasn't done the facilitated diffusion.
So that's osmosis. Let me give you another example of how this works, because usually this takes a couple tries. Let's do another example. Let's take a beaker of water. Oh, I'm sorry, mistake. Autopilot. Beaker of water, and we'll have some red blood cells. Red blood cells inside there. We want to see what's going to happen for red blood cells in a beaker of water. Well, one thing you need to know, and not just for me, just forever, is that the normal human cell of any type is always .9% salt. All of our cells are 0.9% salt. It's just automatic. So it's not something I really need to tell you in the future because it's always true. It's a leftover, it's a residue of our evolutionary days. Our ancestors came out of the ocean. So the early ancestors lived in the ocean, they picked up some salt supply. And then when they left the ocean to come on dry land, they kept the salt. So we still have it now. So obviously, we have the same ancestors as other mammals. So all mammals are 0.9% salt. That's the reason. They all have the same salt supply that we do, for the same reason, same ancestor. At any rate, so 0.9% salt is something you just simply should know. We actually will probably not refer to it again, but you'll see it in other classes and nursing and all the rest of it. You'll see it. So 0.9% salt. The water, of course, is just water. % water, which means 0% salt. I have to confess, these seem to be working. I was skeptical, I said I would try it. Anyhow, 0% salt. And so you would normally think, okay, 0.9% salt in the cells, 0% salt in the water. I shouldn't have said anything. Anyhow, so you'd expect the salt should go from high concentration into low concentration, but it won't because of the cell membrane. So once again, you do the water thing. 100% water in the cell, you would expect 99.1% water. And again, that's always the case. It's never going to change. So it's not something you ever need to figure out or to do anything. It's always that way for all cells. For all cells. So 99.1% water here, 100% water in the beaker. You'd expect under these conditions water to enter into the cell. So under these conditions, it's kind of like blowing up a balloon. You expect the cell to at least dilate. That means to expand or to get bigger, like blowing up a balloon. That's the least that should happen, because water's coming in. Or, if too much comes in, the whole thing just blows up, like blowing up a balloon too much. Now I said under these conditions. 0.9% salt, which again is just automatic for everybody, is isotonic solution. And what that really means is it's the same both inside the cell and outside the cell. That's really what isotonic is. The same inside and outside. But for us, isotonic solution is 0.9% salt. Anything below 0.9, down to 0, is hypotonic. Now, hypo means below or underneath, like hypodermic needle, they're going under the skin. So this is below or underneath 0.9. So technically, I could have done 0.8. Or 0.7. I did 0 because I felt like it. So what I can now say is, under hypotonic conditions, which means that the concentration outside the cell is less than inside the cell. We're talking salt now. The concentration outside is less than inside. Under hypotonic conditions, water goes into the cell, and the cell at least dilates, if not blows up. Yeah. Under hypotonic conditions, and that means the salt concentration, or it could be anything else, glucose, whatever. The salt concentration outside the cell is less than inside the cell. Under hypotonic conditions, water goes into the cell at least dilates, if not blows up completely, it ruptures. Now, just as I had a concentration below 0.9, we can do one above. Let's do 10% salt. Again, I could have done 1 or 1.1. I could have done anything. I just chose 10. This is hypertonic. Hypertonic conditions. So with 10% salt, hyper means above or higher than. Above or higher than. Again, you're still comparing with 0.9. That's always your starting point. 0.9. So anything above 0.9 will be hypertonic. So now in this case, the salt concentration is higher outside, much lower inside, still 0.9. That's not going to change. So you'd expect the salt to go in. By this time, you recognize it won't because of the cell membrane. So once again now, we'll do the water thing. So 90% water in the solution and 99.1 in the cell. So the water concentration is higher in the cell, lower outside. You expect water under these conditions, under hypertonic conditions, you expect water to leave the cell. The cell should shrink because it's losing water. This is called crenation. A cell under hypertonic conditions undergoes crenation, which means the loss of water causing the cell to shrink. So one more time. Under hypertonic conditions, the cell will undergo crenation, which means loss of water, which makes the cell shrink. But that's for our cells. Bacterial cells do the same thing. There's an extra thing involved. Obviously, all cells, whether ours or bacteria or grass or whatever, have a cell membrane. We all know that. Well, bacterial cells, in addition, have a cell wall. We do not. We do not. It's one of the differences between our cells and bacteria. Now, of course, you know perfectly well bacteria have no nucleus, and we do. But this is another difference. They have a cell wall, we do not. So, when the cell, the bacterial cell, is in hypertonic conditions, the cell will start to shrink. It's going to lose water. So the cell will shrink. But the cell wall does not shrink. So when the cell starts shrinking, the cell membrane tears away from the cell wall. It kills the bacteria. It is crenation. But again, there's this extra structure that we do not have. So when the cell starts to shrink because it's losing water, see, our cells do it too. Our cells shrink. But we have no cell wall. So our cell simply shrinks. That's the end of it. But in this case, for the bacteria, the cell shrinks. The cell wall does not shrink. So the cell membrane, getting smaller and smaller, is tearing away from the cell wall. It kills the bacteria.
So during crenation of a bacterial cell.
Dies. So it's given a special name for bacteria. Plasmolysis. Plasmolysis. Lysis means to split or to rupture. So plasmolysis is crenation. Plasmolysis is crenation. The bacterial cells do plasmolysis, ours do not. Because we don't have cell walls.
So what is the difference between plasmolysis and crenation?
Oh, I just said the bacteria have cell walls, we do not. So our cells just shrink. That's the end. But when the bacterial cell shrinks,